This is from worksheet 6 from Learning Outcome 1 of Engineering Mathematics 3. This is a worksheet looking at second order parametric differentiation. In question 2c, we're asked to find the turning point of the curve that's defined by these functions for x and y, and determine the nature of any turning points we find here. We know in differentiation to find turning points, we find the first order derivative of y with respect to x, and in order to determine the nature of such turning points, we need to find the second order derivative. As parametric differentiations, we'll follow all the steps we normally do when tackling such a problem. The first of which being to find the first order derivatives of dx and dy with respect to t. So dx by dt is going to be equal to 2t minus 2 over t squared, and dy by dt is equal to 2t plus t over 2 squared. And I'm sure we're all quite happy with t squared being becoming 2t as a derivative. But remember, when we have something over t, that's effectively t to the power minus 1. So that's where our sign change is coming from. And when we decrease our power, well, with 1 over t becomes 1 over t squared, because that's a power of minus 1 going to a power of minus 2. So we have our two derivatives, and parametric differentiation tells us this is the relationship which will give us dy by dx. Just an application of the chain rule, and we can write dy by dt divided by dx by dt, which will reduce to give us dy by dx. Now we have both of these, we can put them into this equation here, and we have 2t plus 2 over t squared at the top, and we have 2t minus 2 over t squared at the bottom. And so we could seek to tidy this up a little bit. And I think the simplest way to do this is to multiply top and bottom by t squared. Because we can do that, we can multiply top and bottom by the same, we still get the same fraction. So this becomes 2t cubed plus 2 over 2t cubed minus 2. And you might observe there's one further simplification that we can readily make, and that's to divide through by 2. So we can finally write t cubed plus 1 over t cubed minus, tidy that minus sign a bit. So this is our formula for dy by dx. I think a bit of neatness, I'll restate it over here. Now, we are asked to find where we can get the turning points of this function. And we do this by making the first order derivative equal to 0. And so we'll write that. Find, I put tp for turning points, and we make t cubed plus 1 over t cubed minus 1 equal to 0. Now we can multiply both top and bottom here by t cubed minus 1. On the left hand side it's going to cancel top and bottom to give us t cubed plus 1. And of course anything that's equal to 0 multiplied by anything else will give us 0 over here. And then we have t cubed is equal to minus 1. Now the cubed root of minus 1, if we think about it, is going to be minus 1, because minus 1 times itself is 1, but times minus 1 again is minus 1. And there's only a single cubic root we have here, so we've only got one value for t. So we can use this value with our functions for x and y in order to find the one turning point that this function has. So we're going to have x equal to minus 1 squared plus 2 over minus 1. That's going to give us 1 minus 2 equal to minus 1 for x coordinate. And for our y coordinate, we'll have y is equal to minus 1 squared minus 2 over minus 1, which becomes 1 plus 2 equal to 3. And so our turning point is minus 1, 3. And that's the first part of the question. We've determined there is, in fact, one turning point, and using that value for t at which the turning point occurs, where dy by dx is equal to 0, we've found our turning point. Now, we must also determine the nature. And to determine the nature of this function, we're going to have to take the derivative with respect to t of dy by dx and use that alongside the value we've already found for dx by dt. So let's write out what it is that we're looking for here. Well, we'll be using dx by dt, which we've found already. So I'll copy that out and put it down here for reference with this part of the problem. That's 2t minus 2 over t squared. And we need the derivative with respect to t of dy by dx, which is the derivative with respect to t of t cubed plus 1 over t cubed minus 1. So it might become immediately apparent here that this is an application of the quotient rule. We have division of one function by another. We can deal with each one happily enough by itself, but together we need to use our quotient rule. So remember, our numerator, the function top, we denote as u, and our denominator as v. And we find each of, okay, for that sign out, we find each of these with respect to t. So du by dt is equal to 3t squared, and dv by dt, I'll just write that again, dv by dt is also equal to 3t squared, because in both terms, the constant term, plus 1 in the first case, minus 1 in the second case, disappears. So this means we can write out our answer, which will be the value for v, which is t cubed minus 1 times du by dv, which is 3t squared, minus t cubed plus 1, which is the value for u, times 3t squared, because dv by dt is the same. It's all divided by the value for v, which is t cubed minus 1 squared. I think we'll have to do a little bit of tidying up just now, and so we will. And the simplest way is to first of all take a common factor of 3t squared at the top. Pretty sure we're left with t cubed minus 1 minus t cubed plus 1. Be careful with our brackets. Get this all over t cubed minus 1 squared. And if we expand those brackets, or not really expand, if we open up those brackets inside, we have t cubed minus 1 minus t cubed. So our ones are going to, our t cubes are going to cancel, and we're going to be left with minus 1 minus 1 inside the bracket. So positive t cubed and minus t cubed in there, again over t cubed minus 1 squared. And of course, minus 1 minus 1 minus 2. That leaves us with minus 2 times 3t minus 6t over t cubed minus 1 squared. So altogether, a much less nasty looking function than we began with. So our final part of the puzzle, take the value for t, which gives us our turning point, which if you remember, that was, I should write nature here. Nature of minus 1, check, minus 1 of 3, when t is equal to minus 1, and it's when t, that's when d squared y dx squared. Oh, getting ahead of myself. That is dt d by dt of dy by dx, what I should be doing next is finding d squared y by dx squared, which is of course the value we just found, d by dt of dy by dx, divided through by dx by dt. So I nearly skipped a very important step there. That is equal to the value we've just found there, which is minus 6t divided by t cubed minus 1 squared, divided by what we found for our value for dx by dt all that time ago, which is 2t minus 2 over t squared. Again, we might wish to tidy this up a little bit to give us a slightly simpler term to deal with. And again, I'll multiply top and bottom by t squared, which gives minus 6t cubed over t cubed minus 1 squared divided by 2t cubed minus 2. And we can further simplify that to 6t cubed over t cubed minus 1 squared 2t cubed minus 2. Put the minus at the top. I think that's probably the neatest we can make this. So now we can go back to the point I was about to make. So for our turning point, minus 1, 3, at t equal to minus 1, we have d squared y by dx equal to minus 6 minus 1 cubed over minus 1 cubed minus 1 squared 2 times minus 1 cubed minus 2. So on top, well, minus 1 cubed is minus 1 times minus 6 is 6. On the bottom, our first bracket, minus 1 cubed is minus 1. So we'll have minus 1 squared. Here we have 2 times minus 1 cubed, which is minus 1. So we'll have minus 2 in this bracket. So minus 1 is minus 2. Minus 2 squared is 4. Minus 2 times minus 2 is also 4. So left with 6 over 24. Oh, careful. 6 over 16. And we can work this out, but we don't really need to because it's positive. And positive for this implies this is a minimum turning point. So function has minus 1, 3 as a minimum turning point. And a lot of math is involved there, but that completes the question and gives us our answer.